we'll get the slides up there. If anyone is not familiar with BMC, we're a multi-billion-dollar global company that you've probably interacted with and didn't know it. If you used a credit card in the last couple of days, took a flight, ate a piece of Hershey's chocolate, drove a vehicle, whether or not you know it, BMC has impacted your life. We handle massive amounts of data and automation for businesses around the globe, both in the IT space as well as in the OT or manufacturing space. We're going to talk a little bit about how to turn that massive amount of data into some form of actionable insights. Predictive maintenance is one of the many ways to do that. But if I asked each of you, what you did, someone's going to say, hey, we make cars. Someone else is going to say, well, we manufacture these precision parts that go in some widget that's used in agricultural pumps all over the globe. And somebody else is going to say, well, we manufacture, a cardboard box that's precision cut. The reality is, most manufacturers today, whether we realize it or not, we actually produce massive amounts of data. And it's that data that allows us to take and make those products even better. I'm going to talk a little bit about what that data looks like, how to collect it, how to manage it, what's coming on the horizon, because the amounts of data is mind-blowing, and then how we turn that into some real actionable insight. I'm going to cover basically 4 different areas. What does data in manufacturing look like? What are some of the challenges that are tied to it? Some solutions to think about, as well as a couple of our products. I won't dive too deep into our products, it's not really why I'm here. And then some of the trends that you should be thinking about as they're coming. So let's first start with data. I call it the 3 V's: volume, variety, and velocity. Now imagine the number 30 with 15 zeros behind it. That's 30 petabytes. And today, there is a manufacturing facility that produces 30 petabytes of data every day. It's massive amounts of data. In fact, here in Berlin, you have a facility that produces 500 with 12 zeros behind it, 500 terabytes. The Tesla Gigafactory. Massive amounts of data. All modern factories are producing this data. And it's not just coming from things like sensors. The facility that I speak about that has 30 petabytes of data every day has over 50,000 sensors in that facility. But they also have all of the data coming from power, energy, water, which are inputs into that factory. They have all of the IT systems that are tied to human resources and finance that are tied to all of these processes, literally thousands of processes, all being managed, all producing data from different sources. So you have a massive volume of data, massive variety of data. And then the last thing that's really important to understand, which is the velocity, is how quickly that data has to be used to be useful. So in that same factory, 1 millisecond, that's how much time they have to make decisions with that data. It's extreme. 1 to 10 milliseconds is effectively real time. And normal type, what I would call normal, it's around 100 milliseconds, right? So what you're seeing is massive amounts of data from all over the place getting shrunk in terms of how fast it has to be used. That's incredible. And this isn't the future, this is happening right now. So, what are the challenges this presents? I really think about it in 4 different ways, right? So, the first is storage. Now, if you were to try and store 30 petabytes of data in a public cloud, that means every day you're going to add an additional $18,000 a month bill just for the storage of that data. Now, push that over the course of a year and 365 days of data being created, you're talking tens of millions of dollars to be able to store that data. It's cost prohibitive. So you have to think differently about what you're doing with that data. How much of it are you using in real time and throwing away? How much of it are you storing? How are you storing it? And so that creates a set of strategies and challenges that you have to think through. The next is bandwidth. Just by a show of hands, who has unlimited bandwidth in their facility? Nobody, right? Which means that if you have a particular sized pipe, you can only force so much through that pipe. And so where you handle that data becomes important. You can't push it all to the cloud, not only because of the cost, but because of the bandwidth concerns, right? And so what are you going to do with that information? Where are you going to handle it? We talked about latency when I talked about the 1 millisecond piece, but that becomes a very important element in terms of which pieces of this data is actually actionable in real time, which pieces of this data can be useful to me in the future, and what parts of this data actually don't matter at all. You have to think those through. And then finally is resiliency. What happens if the network goes down? You can't have your processes stop. You can't have automated equipment just stop working because the network is down. So you have to build in or think about how resilient your processes are when the data streams are turned off for periods of time. Can you continue to operate, and what are the risks associated with that? So those are some of the challenges that I think we face. So there's a couple of different approaches to take when it comes to this. And one of them is what I refer to as cloud out, and the other is what I refer to as edge in, right? So a cloud out approach is where we try and do as much as we can in the cloud and then extend some capabilities down to the edge. And over the course of the last 10 years, we've all been told that's what we have to do, cloud, cloud, cloud. Well, it doesn't necessarily make sense when we talk about those challenges that we were looking at a few minutes ago. The other is edge in. How do I deploy as much of the technology at the edge and then extend up to the cloud? So let me explain what I mean by this. So you have massive amount of data coming from all over the place. You have latency requirements to hit. So instead of taking all of your information moving into the cloud, information used for decision making gets handled at the edge. Do inference at the edge, machine learning at the edge. Make decisions there. Your data is staying as close as possible to where it's being created. Decisions are being made with it, and then you can decide what to do with it after that. It helps alleviate some of those challenges. In other cases, some of the information isn't being used in real time, isn't being used for decision making. Then you can go ahead and have a hybrid approach where some of this is cloud out and some of this is edge in. So start thinking about how you take these different approaches. So edge in, where you have bandwidth constraints, latency is critical, you have reliability concerns, and I didn't even talk about the privacy or security concerns. You don't want that data going to the outside world, keep it at the edge. If, on the other hand, you live in a world where bandwidth is completely unlimited and tolerancy isn't an issue, then use the cloud all day long. So 2 approaches to think about as you begin to think. So you have all this information. How do you turn it into some form of strategic advantage? I think there's 3 core capabilities that we all need to figure out. The first one is observe. I want to be able to ingest that data, visualize it, display it, distribute it, share it with people who want to be able to understand and see it. It's a pretty basic capability. We all have some form of this in our facilities and in our plants and our businesses. And they usually take the form of a dashboard or something to that effect. Control system with a display. But how do you do that across all of those sources? So how do you bring those together for observability in one place? That's capability number 1. Capability number 2 is, it's not good enough to know what has happened or to know what is currently happening. We need to understand what's going to happen. So we need to be able to predict which means we need to be able to use that data to tell us what's gonna happen, not what has happened. And so that's capability number 2. And I'll talk a little bit about ways to do each of these. And then the last is orchestration. All of this information needs to be able to live across systems and different sets and groups of decision makers. But it also needs to be used for automating processes across systems. And so orchestration becomes a pretty important piece of this, where you don't necessarily want all that data living in silos. You don't want it just to be visualized through some form of observability, but you also want to be able to have it connect and be able to help automate processes in between. I'm going to talk about 2 different types of solutions at BMC. Now, look, there are a lot of solutions on the marketplace. I'm using these as examples. If you want to learn more about these, the sales team at the BMC table would love to talk to you about it. I'm not in sales, so I'll let them deal with that. I really care about what this does for us. So the first is something we call BMC HelixEdge. And I know Peter didn't want to talk too much about AI, but I'm going to show you how AI lives in real world today to do this. And so this is something we refer to as an operational technology management platform. The idea is to be able to collect, aggregate, analyze, orchestrate, and predict across OT assets, but live in both the device world, or the sensors and the SCADA systems, as well as in the land of maintenance systems. So I'm going to use this example. This is a screenshot from a real customer. Actually, a utility company. I chose this, not manufacturing, so that you could see something different somewhere else, because you're probably sick of manufacturing by this point in the day. But this utility company has transformers, those large boxes that sit substations. You see them all over the place. Those transformers are expensive. They cost anywhere between $500,000 and $1 million, the really big ones do. And their biggest challenge or problem is they either fail without knowledge, so you can consider that unplanned downtime if that's what you want to call it, or they don't last as long as they should. So if it's rated for 100,000 operating hours, maybe they only get 90,000, right? Also an expensive proposition. In other cases, they are told to replace those at 100,000 hours, and they do religiously, but did they really need to replace it? So that's the problem set they're starting with, right? And so these transformers can produce a ton of data. They have sensors on them. Everything from the bindings and there's a pump on them. They're filled with oil. And so there's something called dissolved gas analysis. This is a little lesson and something new for the day. When transformers have an energy load, those gases there are certain gases that are dissolved in the oil. And if you can understand and monitor those gases, you can do a couple of things. One, you can tell what type of loads the transformers had in the past. You can also predict when a transformer is going to fail. And you can also predict how much life that transformer still has. And the only real way to do that is using machine learning, which is very basic technology at this point, but very easy to do. That gives you kind of some basic predictive maintenance type scenarios for this, but most of the people working on these transformers are aging out, so the knowledge is going with them. So how do we take this data and turn it into actionable intelligence for people that may not have 30 or 40 years experience working on these? That's where the power of AI comes in. Because what we can do is, we have this basic observability that's going on. We can see all the data and the information. We now have the ability to predict that there's going to be some form of a failure. And in this case, the anomaly was predicted, but then AI turned that information into a plain language assessment of what's actually happening and what you should do about it. That information then has a human decide what they want to do, or because you can orchestrate into other systems like maintenance systems, that information can immediately become a service ticket in a service management system, and it's not just an alert. Now all of a sudden we're starting to take action on that information. So we've gone from just seeing about our transformer to understanding and predicting what's going to happen with this transformer, turning that into information that can be used by a real human, then run it through automations to create all of the processes for service management tickets that turn this into some form of action. So having platforms like this that can take and ingest information from all types of assets, including what I refer to as contextual information. So platforms like this don't just look at the sensor data, they also pull things in like the weather. Maybe the weather's going to have an impact on this thing. It can also take into account things like financial systems. Another use case, I won't share a slide for it. There was a customer of ours wanting to do fleet management. Fleet management, you're usually trying to track an asset, understand how it's being driven or used. And in their case, they wanted to optimize fuel usage. And they thought maybe it was how the vehicles were being driven and maintained. But we also ingested all of the other information associated, so driver information and financial information. And what turned out was, it wasn't a problem with how the vehicles were being driven, it wasn't how they were being maintained, it was actually fuel fraud. It was the fuel service actually not delivering the amount of fuel that they said they were delivering. But because you can combine all of that information, you get those types of insights that you can do very interesting things with. So, platforms like this help you bring together all of that information and hit those three capabilities I talked about. This is great when we're talking about the world of physical assets. But let's move back again into just the realm of data, right? So I have all of this data and information moving around. We also have a solution that we refer to as Control-M. So when I talked about the credit card exercise and the aircraft and all, Control-M is the solution that makes all of this possible. And basically what it is it's a data workflow orchestration tool set that does a variety of amazing things. I won't go into all of those details. Again, the team is in the other room, would be more than happy to talk about it. But what happens in, for example, an auto maker? So, major automaker, actually one here in Germany, applied Control-M to just one production line to be able to orchestrate the data to understand and ensure the SLAs between this information. And instead of going from remediating problems, it turned now into being able to avoid them altogether. This particular use case, one production line, several $1 million of savings every month. So let's talk just a little bit about the future. I think there's really three key areas that you need to begin really diving into and thinking about. I touched very briefly on it, edge computing, as my lengthy title. By the way, my title, Vice President of Operational Technology and Edge Computing, I wrote that title when they told me I could get paid by the letter. So I figured out how to make it as long as I could. Now, I love edge computing, and I can talk about edge computing all day long. But there's some things you should think about. Number one is it's a distributed computing paradigm. It's just is the way you think. It's not new. However, because of the proliferation of sensors and information and those constraints that we talked about, there's a resurgence in how you think about applying edge computing, especially in places like manufacturing. And it requires a different handling of the data, a different thinking about how far you want that information to move, and ultimately a new set of technologies tied to hardware to be able to take advantage of it. The third is data optimization. So, those data sources are exploding. There's an unholy dance that's taking place between AI and data. What I mean by that is massive amounts of data being created become pretty useless if you can't figure out what it's telling you. You need AI. AI becomes pretty useless if that data is messy. And so you need to have clean data for AI to work well. So these two are kind of in this unholy dance, right? Well, AI can actually help with optimizing the data first. And so I think one of the big trends, we see that with the products we're developing and the work that we're doing with our customers, to do things like being able to self-optimize storage systems, what data needs to go where and when, being able to optimize how data is organized in different ways. Think of this in terms of graph databases and things like that. And so as you dive a little bit more into that data optimization topic, you're going to see that AI is empowering us to be able to do different things with data. And it has to happen if we want to be able to leverage AI later when it comes to AI-driven processes, which is where AI making decisions for us or helping us make decisions, whether it's scenario analysis and simulation, whether it's prediction of failure, or whether it's even prediction of how to operate an asset differently to be able to get more life out of it. These things are happening now, but they're going to become even more important as we look forward. So my time is up. I want to thank you all. If you have any questions, happy to take them now or afterwards as well. Thank you.